Human biology is a perfect product of Earth's gravity. Every bone in your body, the strength of your heart, even your sense of balance, were sculpted by a single, unyielding force. But what happens when we step out of that cradle for good? This video will reveal how living permanently on the Moon or Mars will not just change where we live, but what we become. We will uncover the startling biological redesign waiting for our descendants, from lighter skeletons to entirely new senses of up and down. What does it truly mean to call another world home, if home rewrites your very body? That single force is a constant in a world of change. Throughout Earth's history, climates have swung from ice ages to tropical hothouses, atmospheres have shifted their composition, and continents have drifted across the globe. Life has adapted to these dramatic shifts, evolving fur for the cold or lungs for new air. But through all of that upheaval, one rule has never changed: gravity. For 3.8 billion years, every organism that has ever lived, from the smallest microbe to the largest whale, has done so under the exact same pull. This is not a variable condition like temperature. It is the unwavering foundation of our biological reality. Our bodies are not merely accustomed to it. They are architectural masterpieces built in direct response to its demand. Your skeleton is a perfect example. It is not a static frame, but a living, dynamic structure. The constant tug of gravity provides the essential stress that tells your bones to stay dense and strong. Without that daily reminder, the very scaffolding of your body would receive a signal it has never, in all of evolutionary history, been prepared for: a signal to relax. The same principle governs your muscles and your heart. The effort of standing up, of walking against that pull, is what maintains muscle mass and cardiovascular health. Your circulatory system, with its intricate network of veins and arteries, is engineered to fight gravity's downward draw, pumping blood upward to your brain. Even your inner ear, the source of your balance, is a sophisticated fluid-filled gyroscope calibrated for 1G. It tells you which way is down with such certainty that you never even have to think about it. This gravitational constant is so deeply woven into our biology that we are utterly unaware of its presence until it is gone. But what exactly are we stepping into? The Moon and Mars are not simply low-gravity worlds. They are worlds with two profoundly different rules. The Moon's gravity is a mere 1/6 of Earth's, a precise 0.166 times the pull we feel here. On Mars, the pull is stronger, yet still less than half of our own, at 0.376 G. These are not minor variations. They are the fundamental, unchanging parameters of two new environments. Think of gravity not as a setting on a dial, but as the operating system for reality itself. On the Moon, with its gentle tug, everything changes. A jump is not a brief lift, it is a slow, soaring arc. Dropping a tool does not result in a quick clatter, but a languid, almost graceful descent to the floor. Your entire relationship with motion is rewritten. A world of deliberate, floating gestures where momentum is hard to build but even harder to stop. Mars presents a different kind of strangeness. At just over 1/3 of Earth's gravity, movement there would feel deceptively familiar at first, a buoyant, bouncy walk. But the physics are not Earth's physics. A stumble that on Earth would be a quick recovery could on Mars send you tumbling in a slow, uncontrolled roll. The force of a fall is less, but your intuition for judging it, honed over a lifetime on Earth, would be completely off. These numbers, 0.166 and 0.376, are the architects of tomorrow. They will dictate the strain on every bone, the workload for every muscle, the very pressure inside your blood vessels. They are not just numbers on a page. They are the silent forces that will begin the long, slow work of redesigning the human body from the inside out. The first humans to walk on these new worlds will not be pioneers of adaptation, but prisoners of their own biology. Their bodies will arrive as perfect Earth machines, expecting a familiar pull that simply is not there. And without that constant gravitational stress, the systems that have kept us healthy for millennia will begin a quiet, alarming process of decay. This is not evolution in action. It is the body interpreting an absence of signal as permission to dismantle itself. The most dramatic change will happen to the skeleton. In the low gravity of the Moon or Mars, bones no longer need to be dense pillars supporting weight. The cells that build bone receive no daily reminder to work, while the cells that break it down continue their normal cycle. The result is a rapid, steady loss of bone mineral density, a condition similar to osteoporosis back on Earth. An astronaut on the International Space Station can lose around 1 to 2% of their bone mass per month in key areas like the hips and spine. For a permanent settler, this is not a 6-month health concern. It is a lifelong, unrelenting trend. Without intervention, the very framework of the body could become brittle and fragile over years, turning a simple stumble into a life-threatening fracture. This skeletal weakening is mirrored in the muscles. Our muscles, especially the large anti-gravity muscles in our legs and back, are in a constant state of low-level engagement just to keep us standing upright. Remove that need, and the body, always seeking efficiency, stops investing precious energy in maintaining what it sees as unnecessary tissue. Muscle fibers begin to atrophy, shrinking in size and strength. The heart itself is a muscle, and it too will decondition. In lower gravity, it does not have to work as hard to pump blood against the pull of the Earth, so it can become weaker over time. This sets the stage for a dangerous scenario. A return to higher gravity, even a visit back to Earth, could overwhelm a cardiovascular system that has grown accustomed to an easier life. Perhaps the most immediate and visible change, however, is one of fluid dynamics. On Earth, gravity pulls our bodily fluids downward, pooling them in our legs and feet through the day. In microgravity, this pull vanishes and fluid redistributes evenly throughout the body, rushing upward toward the chest and head. Settlers will likely experience a persistent facial puffiness, a stuffy nose, and thinner legs as their bodies adjust to this new fluid map. While this shift might level out over time, it places new stresses on the eyes and the brain and is a constant physical reminder of a world out of balance. For these first generations, every one of these changes is a health problem, not an adaptation. Their existence will be defined not by embracing a new normal, but by a constant, exhausting fight against their own biology. Their days will be structured around artificial replacements for gravity, rigorous daily exercise regimens with specialized resistance machines to trick their muscles and bones into thinking they are still under load, and likely a cocktail of medications designed to slow bone loss and support cardiovascular health. They will live in a state of managed decline, their well-being dependent on technology and discipline just to maintain a baseline that Earth provides for free. But all of these challenges apply to the adult human body, a finished product suddenly placed in a new environment. The real biological turning point will come not with the first settlers, but with their children. The ultimate test of a permanent off-world civilization is not if adults can survive there, but if life can begin there. Human reproduction in a low-gravity environment is perhaps the greatest unknown in our entire interplanetary future. We have fragments of troubling data from animal studies conducted in the weightlessness of orbit. Research on mice and rats has shown that the earliest stages, the delicate dance of fertilization, and the initial divisions of the embryo can be profoundly disrupted without gravity's guiding hand. The proper formation of the embryo's axis, which determines where the head and tail will form, seems to rely on gravitational cues we are only beginning to understand. In microgravity, this process can go awry, leading to developmental failures. This raises a daunting specter for the first generation hoping to build families on the Moon or Mars. Yet here is where the story shifts from terrifying to fascinating. Permanent lunar and Martian bases will not offer the chaotic free fall of orbit. They provide something entirely new, a stable, gentle, but persistent pull. The question is not how Earth biology fails in 0G, but how it might rewrite its own blueprint in 0.376 or 0.166G. From the very first cell division, a developing human in these environments would be following a different set of instructions. The most obvious changes would be in the systems built to resist gravity. On Earth, a fetus's skeleton and muscles develop under the constant, muffled pressure of the amniotic fluid and the mother's own movements, a preview of the world to come. In lower gravity, the signals that tell stem cells to become dense bone or powerful muscle fibers would be quieter. The developing body might invest less in structural mass from the very beginning, creating a lighter, more delicate skeletal frame that is perfectly adequate for its low-G world but would be catastrophically fragile on Earth. The vestibular system, the inner ear balance center, would calibrate itself to a different standard. On Earth, the pull that orients a toddler's first steps is absolute. On Mars, that pull is gentler, and on the Moon, it is faint. A child born and raised there would develop a sense of balance tuned to that specific environment. Their up and down would be based on a softer truth, making them potentially clumsy and disoriented in a full 1G field, but granting them an intuitive, graceful mastery of their native low-gravity world. This is the pivotal moment where hardship for the parents becomes a new normal for the children. Their bodies would not be fighting decay, but following a developmental pathway laid down by a new planetary constant. They would be the first humans whose biology is not borrowed from Earth, but authored from conception onward by the silent, gentle pull of an alien sky. A child taking their first steps on Mars would be learning a different kind of balance. Their entire journey from infancy to adulthood would unfold under a gentler sun, guided by a softer hand. Pediatric development, that intricate and precisely timed symphony of growth, would be conducted to a new tempo. The most visible signature of this new world would be written in their stature. On Earth, the long bones in our legs and spine grow under the compressive force of our own weight, a force that subtly guides their final shape and density. In lunar or Martian gravity, that compressive force is dramatically reduced. Without the constant, heavy pressure, growth plates might remain active for a longer period, potentially allowing for greater longitudinal bone growth. Combined with a lighter skeletal structure requiring less dense mineralization, the result could be a generation of notably taller, more slender individuals. Their proportions might shift with longer limbs relative to their torso, a body plan optimized for efficient movement in a world where jumping is easy and falling is slow. This is not a guarantee, but a fascinating possibility, a direct anatomical response to a lifelong reduction in load. Their muscular development would follow a parallel path. A child on Earth builds muscle mass through the simple act of moving against gravity, crawling, then walking, then running. Each of these milestones is a resistance workout. For a child on Mars, that same playful activity provides only a fraction of the resistance. Their bodies, programmed for efficiency from the start, would likely accrue less bulk, developing leaner, more endurance-focused musculature rather than the powerful bursts of strength needed on Earth. Their calf muscles, which work constantly here to propel us upward, might be less pronounced. Their back muscles, which brace our upright posture, might be more streamlined. They would be strong for their world, but their strength would be of a different kind. The most profound adaptation, however, would be invisible, etched into their nervous system. Proprioception, your body's internal map of where all its parts are in space, is calibrated by countless tiny sensors in your muscles and joints. From day one, a Martian child's brain would be building that map with different data. The feedback from lifting an arm or taking a step would signal a lighter limb moving through a less resistant medium. Their sense of their own body's weight and inertia would be fundamentally alien to an Earthling's. Even more critical is the vestibular system, the inner ear gyroscope. On Earth, its fluid responds definitively to gravity's unwavering pull, giving us an absolute sense of down. For a child growing up where that pull is only a gentle suggestion, their brain would learn to integrate weaker signals with visual cues and touch to construct their sense of orientation. Their down would be a consensus, not a command. This generation would be the first in human history whose entire physical and neurological baseline was authored not by the deep well of Earth, but by the shallow gravity of an adopted home. They would look up at a pink sky or a stark, star-filled black and feel, in their very bones, that they were exactly where they belonged. This new baseline of development sets the stage for a transformation measured not in years but in generations. The true power of a new environment is not in how it changes a single body, but in how it rewrites the genetic instructions passed down through time. For the human skeleton, this means a fundamental redesign. On Earth, our bones are masterpieces of compromise, dense enough to handle the stress of a fall or the load of a sprint, yet light enough to allow for efficient movement. This balance is maintained by a simple biological rule: use it or lose it. The constant mechanical loading from gravity, from the pressure of each step, sends tiny electrical signals through the bone matrix, telling specialized cells to deposit fresh calcium and minerals, reinforcing the structure. Remove that daily demand and the signal fades. The cells that build bone become quiet, while the cells that resorb it, breaking it down to release minerals into the bloodstream, continue their work. The result is a net loss, a skeleton that slowly erodes from within. For permanent settlers, this is a medical condition to be fought with exercise and medicine. But for their descendants born into that gentle pull, evolution begins to ask a different question. Why build a fortress when you live in a world without siege? Over centuries, the relentless pressure of natural selection would favor individuals genetically predisposed to a lighter, more efficient skeletal framework. These would not be brittle bones, but bones perfectly optimized for their new reality. The architecture would change. Think of the difference between the dense, solid leg bone of an elephant and the lighter, more hollowed structure of a bird's bone. Both are incredibly strong for their purpose, but one is built for constant, crushing load and the other for lightweight flight. A human skeleton adapting to permanent lunar or Martian life might trend toward the latter principle. Bone density could decrease overall, not as a failure, but as an intelligent reallocation of resources. The distribution of that density would also shift. Areas that bear the most weight on Earth, like the vertebrae in the lower spine or the neck of the femur in the hip, might see the most dramatic reshaping. These critical junctions might develop a different internal architecture, becoming more porous like a sponge or honeycomb at their core, but retaining a strong, dense outer layer for protection. This trabecular bone, as it is called, provides tremendous strength for its weight, a perfect adaptation for a world where loads are lighter, but the risk of impact from a fall or accident still exists. Certain structural reinforcements we carry today might simply fade away as unnecessary genetic baggage. The pronounced ridges and bumps on our bones, where heavy muscles anchor and pull against gravity, might become smoother, less defined. The curvature of our spine, which acts as a shock absorber for our upright posture under 1G, might subtly straighten over generations when that compressive force is lessened. Even the shape of the skull could be influenced, as the muscles of the neck that constantly work to hold our head upright against gravity's pull become less massive, requiring less robust anchoring points. The result, after many generations, would be a human form that appears more graceful and elongated, with a lighter, more delicate frame. They would not see themselves as fragile, any more than a heron sees its slender legs as weak. They would be built for the world they live in, where movement is a series of fluid, buoyant gestures, and the skeleton is no longer a heavy pillar, but a minimalist, elegant scaffold, perfectly tuned to the gentle, persistent whisper of a foreign gravity. A lighter skeleton demands a different kind of engine. The powerful muscles that define an Earth athlete, the bulging calves and thick quadriceps that propel us upward against gravity's full weight, would become relics of a bygone era on a world with a softer pull. Evolution is a ruthless accountant, and it does not invest in infrastructure it does not need. Over generations, the genetic blueprint for these massive anti-gravity muscle groups would be quietly edited. Why carry the metabolic cost of maintaining explosive power for jumps you will never make, or for supporting a body weight that is only a fraction of what it once was? The selection pressure would shift decisively from raw power to supreme efficiency. The settlers of Mars or the Moon would not become weak, but they would become specialized. Their musculature would likely trend toward long, lean fibers built for endurance rather than short, bulky fibers for bursts of strength. Think of the difference between a marathon runner and a weightlifter. Both are phenomenal athletes, but their bodies are optimized for entirely different tasks. The off-world human would be the marathoner of low gravity, engineered for sustained activity over vast, dusty plains or through intricate lunar lava tubes where stamina matters more than a single powerful leap. This shift would redefine the very silhouette of the human form. The pronounced V shape of a strong back, built to stabilize the torso against Earth's pull, might soften. The powerful glutes and hamstrings, which work constantly here to keep us from folding forward, would become less pronounced. Even the neck muscles, which constantly engage to hold our heavy heads upright, might slim down. The body would shed the bulk designed for a constant fight, streamlining itself for a world of floating ease. But efficiency does not mean simplicity. In fact, the new physical demands of these worlds would cultivate a different kind of muscular intelligence. While lifting a heavy piece of machinery becomes easier in low gravity, its mass and inertia remain the same. Moving it requires careful control rather than brute force. A sudden shove could send both the object and the person flying in opposite directions in a slow-motion disaster. The critical skill becomes precise, deliberate movement, especially when encased in a bulky pressure suit that turns every gesture into a careful negotiation. This environment would place a premium on exquisite fine motor control. The small, dexterous muscles of the hands, forearms, and shoulders would be in constant use, maneuvering tools, operating delicate controls, and managing the subtle balance of objects with unfamiliar weight. Generations born into this reality might develop a heightened neurological connection to these muscle groups, granting them a surgeon's precision inside their cumbersome gloves. Their strength would not be displayed in a deadlift, but in the steady, unwavering hand that can assemble a complex instrument in a vacuum, or in the enduring grip that can traverse a rocky Martian slope for hours without fatigue. They would be artisans of momentum, their strength hidden in control and endurance, a perfect biological reflection of a world where every action has a longer, slower consequence. Yet the most vital pump in the body, your heart, would also be redesigned by this gentler world. On Earth, your heart is a powerful muscular engine, and one of its most demanding jobs is a constant, silent battle against gravity. Every beat must generate enough pressure to lift blood from your feet and legs all the way up to your brain, fighting that downward pull with every single cycle. This is the hydrostatic pressure gradient, a fundamental force your entire circulatory system is built to manage. On Mars or the Moon, that gradient, that steep hill the heart must climb, becomes a gentle slope. The heart no longer needs to be a powerful uphill pump. Over generations, the relentless logic of efficiency would apply here too. A heart that does not need to work as hard to achieve the same circulatory goal could become smaller and less muscular. It would be a more efficient, endurance-tuned organ, beating steadily to circulate blood through a body under less physical stress, a quiet engine in a calm world. But the change would not stop at the heart size. The entire vascular system, the vast network of arteries and veins, would need to recalibrate. On Earth, our veins are equipped with a series of one-way valves, and our leg muscles act as secondary pumps, squeezing blood upward against gravity's persistent drain. In a low-gravity environment, this elegant system becomes largely unnecessary. Blood returns to the heart with far less effort. The complex hormonal and neurological systems that tightly regulate our blood pressure on Earth, constantly adjusting for whether we are lying down or standing up, would be receiving entirely different data. The very concept of orthostatic intolerance, the dizziness we can feel when standing up too fast as our body struggles to adjust blood flow, might fade from the medical lexicon of these new civilizations. Their bodies would learn a new normal for fluid distribution and pressure, likely stabilizing at a lower overall blood pressure that is perfectly adequate for their needs. This rewiring presents one of the most intriguing puzzles. If a Martian descendant were to ever visit Earth, their cardiovascular system would face a crisis. Their smaller heart would strain against the sudden, crushing demand of Earth's gravity. Their blood, accustomed to flowing easily in a gentle gradient, would pool heavily in their legs, their vascular tone insufficient to fight the pull. They might experience profound dizziness, a risk of fainting, and potentially even cardiac stress, trapped in a gravity where their biology had long since forgotten how to climb. Their heart, perfectly evolved for the soft skies of Mars, would be utterly overwhelmed by the deep, familiar gravity of humanity's ancestral home. But this new cardiovascular reality is just one layer of a deeper, more profound sensory rewrite. Perhaps the most intimate change of all will occur in the very way a person perceives their own body and its place in the world. On Earth, your sense of balance is an absolute certainty. You close your eyes and you still know which way is down. This is the work of your vestibular system, a tiny, fluid-filled labyrinth deep within your inner ear. As you move, the fluid sloshes, bending microscopic hair cells that send precise signals to your brain. Gravity provides the constant, unwavering reference point, the true north for your personal gyroscope. On Mars or the Moon, that reference point is softened to a whisper. For a child developing in that environment, their brain must learn to navigate without a strong gravitational anchor. The vestibular signals would be fainter, less definitive. To compensate, their neural circuitry would learn to rely more heavily on other cues, weaving together a tapestry of orientation from what they see and what they feel. Visual landmarks would become paramount, the horizon line a critical anchor, the sensation of their feet on the ground, the pressure of a hand on a railing. These tactile inputs would carry greater weight in the brain's calculation of up and down. Their sense of balance would become a collaborative effort, a consensus built from multiple sources, rather than a single, authoritative command from the inner ear. Over generations, this shift in reliance could lead to a physical change in the vestibular organ itself. Just as unused muscles atrophy, the delicate structures tuned to detect a strong gravitational pull might become simpler, less sensitive. It would be a sensory organ adapting to a quieter world. This recalibration extends inward to proprioception, your body's internal map. Right now, without looking, you know if your arm is bent or straight. This map is built from millions of sensors in your muscles and joints, constantly reporting position and tension back to the brain. For a person born in low gravity, the data flowing into this map is fundamentally different. Lifting an arm requires less effort, the limb itself feels lighter, its inertia unfamiliar. From their first clumsy reach as an infant, their brain is charting a territory of reduced resistance and altered momentum. Their neural map would not include the deep, familiar strain of Earth's gravity. The consequence of this sensory redesign would be starkly revealed if a Martian-born human ever set foot on Earth. It would not be a simple case of space sickness, a temporary dizziness from conflicting signals. It would be a profound, existential disorientation. Their brain's entire system for understanding orientation, a system built on visual and tactile consensus in a gentle gravity field, would be violently overridden. Earth's powerful, undeniable pull would flood their attenuated vestibular system with a signal it was never built to process. Their proprioceptive map would be a lie, every movement feeling crushingly heavy and wrong. They might struggle to simply stand upright, their muscles firing in incorrect sequences, their brain unable to reconcile the overwhelming gravitational truth with a lifetime of softer data. They would be a sailor from a calm sea thrown into a hurricane, their internal compass spinning wildly, seeking a north that no longer exists for them. Their disorientation would be neurological, the deep confusion of a mind living in a body whose core operating system has been replaced. But the story of our internal fluids goes far deeper than the heart and blood vessels. Beneath the skin, a second, silent circulation is at work, one that is even more dependent on Earth's unyielding pull. This is the lymphatic system, a vast network of delicate vessels that weaves through your tissues, collecting excess fluid, cellular waste, and pathogens. Unlike the blood pumped by the powerful heart, the lymph has no central engine. Its movement relies almost entirely on two forces: the gentle squeezing of your muscles as you move, and the constant downward assist of gravity. On Earth, this elegant partnership works so seamlessly we never think of it. Every step you take, every subtle shift in posture, acts like a pump, pushing this clear fluid upward through one-way valves, slowly filtering it back into your bloodstream. Gravity ensures the fluid drains downward into these vessels to begin with. In the gentle gravity of the Moon or Mars, this entire system faces a quiet crisis. The primary driver for drainage, gravity's pull, is drastically weakened. The secondary driver, the muscular pumping action, is also reduced in a world where movement requires less effort. The result could be a slow, pervasive stagnation. Excess interstitial fluid, the fluid that bathes your cells, might not drain properly. Cellular waste products could accumulate in the tissues. Even the circulation of crucial immune cells which patrol these lymphatic highways could become sluggish. For early settlers, this presents a host of long-term health challenges. Persistent, low-level edema, a subtle swelling in the limbs, could become a common complaint. The body's ability to fight off local infections or clear away the byproducts of normal metabolism could be impaired, creating a constant, low-grade burden on overall health. It is a problem of subtle clogging, a gradual slowing of the body's internal cleanup crew. Yet, over generations, this very stagnation could become the engine for a remarkable adaptation. If the environment does not provide the force to move fluid, biology may engineer its own pumps. One possibility is a muscular evolution within the lymphatic vessels themselves. Tiny, smooth muscle cells embedded in the vessel walls, which currently only provide passive tone, could become more active and coordinated. They might develop the ability to generate slow, rhythmic waves of contraction, a peristaltic motion similar to how your intestines move food, actively propelling lymph fluid along its path independent of gravity or limb movement. The body might also develop a denser, more prolific network of these vessels, creating shorter, more efficient drainage pathways to compensate for the weaker flow. The very structure of our tissues could change. The interstitial spaces themselves, the gaps between cells, might become slightly more pressurized or structured to encourage directional fluid movement toward these active lymphatic pumps. It is a vision of the body becoming its own active fluid management system, no longer a passive vessel relying on a planetary force, but a self-contained, dynamically balanced biome. The descendants of Mars might not just have lighter bones and leaner muscles, but a fundamentally rewired plumbing system, one that hums with a quiet, internal rhythm, tirelessly cleaning and balancing their bodies in a world that offers no gravitational assistance. The difference between Mars and the Moon is not just a matter of distance, but a fundamental fork in our biological future. While both are low-gravity worlds, their specific pulls, 0.376 and 0.166, are not merely points on a scale, they are gateways to two entirely different ways of being human. Mars, with its stronger gravity, offers a path that might still feel somewhat familiar. The pull there is strong enough to allow for a recognizable upright posture and a gait that, while bouncy, would still be a walk. You could likely stand comfortably, your body's weight distributed in a way your Earth-born brain could intuitively understand. Movement would be energetic and springy, a kind of perpetual low-gravity jog where each step propels you forward with an easy momentum. Over generations, this could refine into a highly efficient, loping stride, a graceful and sustainable way to traverse the vast, open plains. The body would adapt to this rhythm, favoring long, elastic tendons in the legs that store and release energy with each bound, and a posture that leans slightly forward to manage that forward momentum. Mars might produce a lineage of endurance roamers, their biology optimized for distance and exploration under a gentle but persistent sky. The Moon, however, presents a far more alien proposition. With only 1/6 of Earth's gravity, the very concept of walking as we know it begins to break down. The force keeping your feet firmly planted is so faint that a normal walking motion could easily launch you into a slow, uncontrolled hop. Maintaining balance during a standard step would require constant, careful micromanagement, an exhausting fight against physics. For permanent lunar settlers, especially over the long term, alternative forms of locomotion would not just be convenient, they would become biological necessities. The most likely outcome is a skipping or loping gait where both feet leave the ground in a rhythmic, bounding pattern. This uses the Moon's weak gravity to its advantage, turning each push-off into a controlled, floating arc. Over centuries, this would reshape the human form from the ground up. The anatomy of the leg would change dramatically, with even longer limbs and a foot structure that acts more like a springboard than a platform. The calf muscles might become less about power and more about fine-tuned control for landing. The hips and spine would adapt to absorb the different impacts of a bounding landing rather than a heel-to-toe roll. Assistive mobility might even become ingrained, not as a tool for the injured, but as a standard way of life. Using poles for stability and added propulsion, or even small personal thrusters for precise movement between structures, could become second nature, their use shaping muscle development and coordination from childhood. The lunar human might evolve into a being for whom Earth-style walking seems as awkward and inefficient as walking on our knees would seem to us. These divergent physical realities mean that after several hundred years, a Martian and a lunar human might struggle to recognize each other's movement as fully human. A visitor from Mars with their efficient lope would appear heavy and ponderous on the airless Moon, their Martian-adapted muscles fighting to prevent each step from becoming a wild leap. A lunar native visiting Mars, in turn, would likely move with an exaggerated, floating caution, their body expecting a gentler return from each hop and finding the stronger Martian pull unsettlingly abrupt. Their skeletons, musculature, and even their neural pathways for balance would be tuned to different gravitational melodies. One is a variation on an Earth theme, the other is a completely new composition. This is the profound lesson of these numbers, 0.376 and 0.166. They are not just environments, they are evolutionary directors, patiently guiding the human body down two separate paths toward two distinct futures under alien suns. This divergence leads us to a profound and unsettling question. Is there a point of no return, a gravity threshold below which a human body can no longer remain biologically compatible with Earth? This is not about comfort, but about fundamental physiological function. Could Martian gravity, at just over 1/3 of Earth's, be just enough to keep our biology within the same broad family tree, while the Moon's gentler pull irrevocably splits our lineage in two? The concept of a threshold is critical. Our bodies are resilient, but they are not infinitely adaptable. There may be a minimum gravitational load required to maintain the basic architectural principles of an Earth-evolved human. Below that line, the body's systems would drift so far from their original design that a return to full Earth gravity becomes biologically impossible, not just difficult. Think of it not as a locked door, but as a widening chasm. With each generation born in a lower gravity field, the biological distance from Earth increases. The bones grow lighter, the heart adapts to a gentler workload, the neural maps forget the old signals. At some point, the chasm becomes too wide to cross. Mars sits in a fascinating, precarious zone. At 0.376 g, it just might be above that critical line. The pull is strong enough to maintain a recognizable upright posture and a circulatory system that still understands the concept of uphill. While a Martian-born human would face severe challenges visiting Earth, requiring extensive preconditioning, mechanical assistance, and likely medical supervision, their core biological blueprint might remain similar enough to make the ordeal survivable. They would be like a deep-sea diver ascending from the abyss, needing slow, careful decompression to reintegrate into a heavier world. There is a chance, however slim, that Martian humans could remain part of a single, if strained, biological continuum with Earth. The Moon tells a different story. At 1/6 of Earth's gravity, it almost certainly falls below the hypothesized threshold. The forces are simply too weak to preserve the integrity of our Earth-bound systems over multiple generations. The skeletal structure would become too delicate, the cardiovascular system too specialized for a nearly absent load, the sense of balance too detached from a strong gravitational truth. A true lunar native, born and raised in that gentle field, would likely find Earth's gravity not merely uncomfortable but lethal. Their body would be an exquisitely adapted machine for a world of floating grace, and placing it under the crushing weight of 1 g could cause catastrophic structural failure, bones fracturing under their own Earth weight, a heart unable to generate sufficient pressure, a brain utterly lost in a sensory storm. For them, Earth would cease to be a home and become a hostile, inaccessible planet. They would be the first members of a permanently separate human lineage, biologically exiled from the world of their ancestors by the gentle, unyielding mathematics of gravity. This threshold, wherever it lies, represents the most significant fork in the road for our species. It is the line between a future where humanity remains one biological family, spread across planets but still connected by shared physiology, and a future where we speciate, branching into distinct forms shaped by the gravity wells of our adopted homes. The choice of which world to settle permanently is not just a choice of landscape or resources. It is a choice about the very definition of human in the centuries to come. Will we remain visitors in low gravity, fighting to preserve our Earth-born selves, or will we embrace a new identity, allowing the silent pull of an alien world to rewrite us from the inside out? The gravity of our new homes will decide. This biological divergence sets the stage for one of nature's oldest and most powerful processes. When populations of the same species become separated and adapt to different environments over long periods, they can slowly become different species entirely. This is speciation, the engine of biodiversity on Earth, and it could very well become the story of humanity's future among the stars. The physical changes we have explored are not just interesting curiosities, they are the raw material for this profound split. A lighter skeleton, a recalibrated heart, a rewired sense of balance, these are not temporary adjustments but the foundations of a new biological normal. Over centuries, these traits would become encoded, favored by the simple fact that they work best in that specific gravity field. An individual with denser, Earth-like bones on Mars would be carrying unnecessary metabolic weight, a disadvantage over generations. Natural selection, even in a technologically managed society, would quietly favor efficiency. But the true driver of speciation is not just adaptation, it is isolation. And the distance between Earth, Mars, and the Moon provides the most absolute isolation imaginable. The journey between these worlds is not a casual trip, it is a monumental, expensive, and dangerous undertaking taking months or even years. For the vast majority of settlers and their descendants, their home world will be the only world they ever know. This physical separation prevents gene flow, the mixing of genetic material that keeps a population unified. A Martian population and an Earth population would simply not be interbreeding. Their evolutionary paths would drift apart, guided by different gravitational masters. This isolation could be intensified by intentional choice. If genetic interventions are used to help future generations thrive in low gravity, perhaps by preemptively strengthening bone formation pathways or optimizing cardiovascular function for that environment, it would introduce deliberate genetic differences. These engineered advantages for life on Mars could become disadvantages for life anywhere else, deepening the divide. The result, after enough time, is not just cultural or political separation, but a fundamental biological incompatibility. Reproduction between an Earth-adapted human and a fully adapted Martian human might become impossible, or at the very least fraught with severe challenges. Their bodies would be operating on different developmental blueprints, the hormonal signals that guide a pregnancy, the physiological demands on the mother's body, even the gravitational cues needed for proper fetal development, could be so mismatched that a successful natural conception and gestation between the two lineages becomes biologically unviable. They would be separated not by animosity but by the silent, unyielding rules of physiology. They might look upon each other with recognition, sharing history, language, and curiosity, but their very biology would whisper that they are no longer the same. They would be neighbors in the solar system, yet inhabitants of distinct branches on the tree of life, their paths forever altered by the gentle, persistent pull of an alien sky. The initial settlers stepping onto Martian soil will be more than just explorers. They will be the genetic founders of an entire new branch of humanity. This presents a profound biological twist known as the founder effect. A permanent colony will not begin with millions, but with perhaps a few hundred carefully selected individuals. Their collective genetic makeup, with all its unique strengths and hidden variations, becomes the entire starting library for a new civilization. Every rare trait they carry, from a particular immune system marker to a specific metabolism, will be amplified in the generations that follow, simply because there are no other genes to dilute them. This random sampling effect could stamp the future population with unexpected characteristics, quirks of biology that have nothing to do with Mars itself, but everything to do with the small, unique group who first dared to call it home. Yet, relying on this slow, random genetic drift and the leisurely pace of natural selection would be an immense risk for a fragile off-world society struggling to survive. The challenges of low gravity are too immediate, too dangerous to leave to chance over millennia. This is where our story takes its most deliberate turn from random evolution to directed design. It is almost certain that these early communities would turn to intentional genetic editing to safeguard their children. Germline engineering, making precise changes to the very DNA of embryos, would offer a way to pre-adapt the next generation to their new world. The goal would not be to create superhumans, but to solve clear and present biological problems. Scientists could introduce genetic variations that promote stronger bone density despite the lower gravitational load, or tweak the cardiovascular system to better regulate blood pressure in a gentle gravity field. They might even address the lymphatic stagnation issue by encouraging the development of more active vessel networks from the very beginning. This is evolution with a purpose, accelerated from a process spanning hundreds of generations into a single lifetime. It represents a fundamental shift in our relationship with our own biology. For billions of years, life adapted to the environment. On Mars and the Moon, we would begin adapting the environment within us. This directed evolution would create a lineage that is not merely surviving in low gravity, but is fundamentally optimized for it from conception. Their advantages, however, would come with a profound cost, a deepening of the biological divide. These engineered adaptations, perfect for life under a pink sky, could render a return to Earth not just difficult, but a physiological impossibility for their descendants. The founder effect gave them a random starting point, but directed genetic editing would set their course, steering the human form decisively toward a new and permanent normal, authored as much by human intention as by the silent pull of an alien world. But this skeletal redesign creates a profound nutritional puzzle. On Earth, your bones act as a vital mineral bank, constantly storing and releasing calcium to keep its level in your blood perfectly balanced. This balance is managed by a delicate hormonal dance led by the parathyroid glands in your neck. When blood calcium dips, these glands release parathyroid hormone, which signals your bones to release some of their stored calcium and tells your kidneys to conserve more. It is a beautiful, self-regulating system built for a world where bones are under constant stress and need to be dense reservoirs. In the gentle gravity of Mars or the Moon, that entire system faces a confusing new reality. The bones, no longer needing to be dense fortresses, will stop demanding such large deposits of calcium, yet the body will still be ingesting this essential mineral through food. This creates what we might call the calcium paradox. The skeletal bank is closing its vaults, but the mineral supply keeps arriving. Without the bone's massive daily withdrawal, calcium begins to accumulate in the bloodstream. This condition, hypercalcemia, is not a minor issue. Excess calcium in the blood can lead to kidney stones as the kidneys struggle to filter out the overload. It can cause bone pain and muscle weakness, and in severe cases, it can even interfere with heart and brain function. For permanent settlers, this turns a fundamental nutrient into a potential toxin. Their diet would need a radical overhaul. They might need to drastically reduce their intake of calcium-rich foods like dairy products and certain leafy greens, a bizarre reversal of everything we are taught about bone health on Earth. Their food systems would have to be engineered not for sufficiency, but for precise limitation, creating a cuisine deliberately low in a mineral we currently see as universally beneficial. Over generations, this paradox would force an evolutionary rewrite of the body's internal chemistry. The parathyroid hormone system, the master regulator of calcium, would be under new pressure. Its old commands telling the bones to release calcium would become dangerous in a world where the bones are not a reliable sink. Natural selection would favor individuals whose hormonal systems adapted to this new mineral economy. The parathyroid glands might become less sensitive, releasing less hormone overall. The body could develop new pathways to excrete excess calcium more efficiently, perhaps through the digestive system. Vitamin D metabolism, which is intimately tied to calcium absorption, would also shift. The very definition of a balanced diet would be rewritten by the silent mathematics of gravity. A meal that strengthens an Earth child could slowly harm a child on Mars, making their culinary heritage a careful, scientific art of mineral avoidance, a daily reminder that their bodies are governed by a different set of fundamental rules. This delicate mineral balance is just one piece of a much larger puzzle, the ultimate question of time itself. How will the gentle pull of a new world shape the very clockwork of our cells and ultimately the human lifespan? The relationship between low gravity and aging is a complex tapestry of potential benefits and profound new threats. On one hand, the reduction in mechanical stress could be a gift to the body. Here on Earth, a lifetime of walking, running, and simply bearing our own weight creates cumulative wear and tear. Our joints, the intricate hinges of knees and hips, slowly degrade under this constant pressure. The cartilage that provides smooth, frictionless movement can wear thin over decades. In the lower gravity of Mars or the Moon, that daily load is dramatically reduced. The forces grinding away at joint surfaces would be far gentler. This could mean a future where conditions like osteoarthritis, so common in Earth's elderly, become rare or even unknown. The skeletal frame itself, freed from the burden of supporting a full Earth weight, might simply experience less structural fatigue over a lifetime. In this way, a low-gravity environment could remove a significant source of physical decline, potentially allowing the musculoskeletal system to remain functional and pain-free for far longer. Yet this potential boon is shadowed by a formidable and constant danger, one that permeates the very air and soil of these new worlds. Space is filled with a relentless rain of high-energy radiation, cosmic rays and solar particles that Earth's magnetic field and thick atmosphere largely deflect. On the Moon, with no atmosphere and only a weak magnetic field, this radiation bathes the surface. Mars has a thin atmosphere and no global magnetic shield, offering only slightly more protection. For settlers, this means a lifetime of exposure to radiation levels far beyond anything we experience here. This is not about a sudden, acute illness, but a slow, insidious assault on the most fundamental level of life. Radiation damages DNA. It breaks the delicate molecular strands inside our cells, creating errors in the genetic code. Our bodies have remarkable repair mechanisms to fix this damage, but they are not perfect. Over time, unrepaired or misrepaired damage accumulates. This accumulation is a primary driver of cellular aging and a key factor in the development of many serious illnesses. The constant radiation environment of Mars or the Moon could, therefore, act as a powerful accelerant for this cellular aging process. It would place the body's repair systems under a perpetual, exhausting strain, potentially leading to earlier onset of age-related conditions and a shortening of the overall health span. But the story grows even more intricate when we consider metabolism, the body's engine. Some research in microgravity suggests that the stress of spaceflight can alter metabolic rates and increase markers of oxidative stress, another form of cellular damage linked to aging. Would a permanent low-gravity environment create a similar, sustained metabolic stress, even after the body adapts? Or conversely, might the reduced physical effort needed for movement lower the body's overall metabolic rate, slowing down some processes in a way that could influence longevity? We simply do not know. This sets up a profound biological tug-of-war. On one side, the gift of reduced mechanical wear, promising stronger joints and a lighter load on the frame for a century or more. On the other, the curse of accelerated cellular decay from radiation and possibly metabolic stress, threatening to undermine the body from within. Which force will prove stronger in defining the lifespan of a low-gravity human? Will they live longer, their bodies preserved by a gentler world, only to have that extra time curtailed by internal damage? Or will advances in shielding technology, medical countermeasures, and perhaps even genetic enhancements to bolster DNA repair allow them to neutralize the radiation threat and claim the full benefit of their low-stress existence? The answer will determine not just how long they live, but the quality of those years, painting a future where old age could be a time of enduring grace or of premature frailty, all under an alien sun. The relentless radiation of space presents a clear danger, but an even more subtle and complex threat may lie in the very soil beneath an astronaut's boots. The human immune system, a finely tuned defense network shaped by millions of years on Earth, will face a dual and unprecedented challenge on another world. It must learn to function in a new gravitational reality while confronting a biological landscape that is either terrifyingly alien or eerily empty. This system, which relies on the precise circulation of cells and the controlled fire of inflammation, could become dangerously confused. In the lower gravity of Mars or the Moon, the basic logistics of immune defense break down. Your white blood cells do not have their own tiny motors. They travel through your body by hitching a ride in your blood and lymphatic fluid. As we have discussed, that fluid circulation becomes sluggish without Earth's strong gravitational pull to assist drainage and flow. Imagine a city's police force suddenly trying to patrol with most of their cars stuck in traffic. The immune cells may simply take longer to reach the site of a potential infection or injury, creating a critical delay in the body's response time. This sluggish circulation is compounded by the strange behavior of the cells themselves. Research from the International Space Station suggests that immune cells can become less effective in microgravity, sometimes failing to activate properly or becoming confused about their targets. In the permanent, stable low gravity of a planetary surface, this dysfunction could become a chronic state, a background noise of immune suppression that leaves the body perpetually vulnerable. The environment these cells must patrol adds another layer of uncertainty. Mars and the Moon are not sterile, but they are incredibly harsh. Any microbial life that might exist there, perhaps hidden in subsurface ice or clinging to existence in protected cracks, would be the product of a completely separate evolutionary history. These would not be germs in the Earth sense, but alien organisms our immune system has never, in all of human existence, encountered. Our defenses are built to recognize familiar patterns, the molecular signatures of earthly bacteria and viruses. Faced with a truly alien microbe, the immune system might not recognize it as a threat at all, allowing it to spread unchallenged. Or, in a more frightening scenario, it might overreact with catastrophic force. Sometimes, when the immune system encounters something utterly foreign, it can panic, unleashing a massive and indiscriminate inflammatory attack known as a cytokine storm. This is not a targeted defense, but a body-wide conflagration that can cause more damage than the invader itself. A simple infection from a Martian organism, harmless in its own setting, could trigger a fatal immune overreaction in a human settler. The opposite scenario, a perfectly sterile environment, carries its own insidious risk. The immune system is a muscle that needs exercise. On Earth, we are constantly exposed to a low level of benign microbes that train and calibrate our defenses. This is the hygiene hypothesis, the idea that a lack of early childhood exposure to diverse organisms is linked to a rise in allergies and autoimmune diseases. A child raised in the ultra-clean, meticulously filtered habitat of a lunar base, on a world with no native biosphere whatsoever, might develop an immune system that has never been properly educated. With nothing foreign to fight, it could turn inward, mistakenly attacking the body's own tissues and leading to a high prevalence of autoimmune disorders. Their defense network, bored and untrained, might start seeing their own joints, skin, or organs as the enemy. over generations, the immune system would be forced to adapt to this bizarre new normal. In response to sluggish circulation, the body might develop more lymphatic tissue locally, at common points of entry like the lungs and digestive tract, creating standing garrisons of immune cells so they do not have to travel far. The genetic regulation of inflammation might be rewired, dialing down the propensity for those dangerous overreactions to unfamiliar stimuli. In a sterile environment, natural selection would favor individuals with a less aggressive, more tightly controlled immune response, reducing the risk of autoimmune diseases but potentially making them more susceptible should a genuine pathogen ever appear. Their immune identity would become a reflection of their world, cautious and efficient in a place of profound biological loneliness, or hyper-specialized to recognize a handful of unique, alien threats. This adaptation, however, would seal their biological divergence. An immune system calibrated for the sterile moon or a specific Martian microbiome would be poorly equipped for Earth, a planet teeming with countless organisms it had never learned to manage. A simple visit could overwhelm them with infections or trigger violent allergic reactions. Their most intimate defense system, the very thing that keeps them alive, would become a barrier, locking them into the biological reality of their chosen world. These profound physical adaptations would not exist in a vacuum. They would resonate upward into the very mind and culture of a new civilization. The human brain is a masterpiece of plasticity, constantly rewiring itself based on the sensory input and physical demands of its environment. For a child growing up on Mars, the very definition of space and effort is rewritten. Their spatial reasoning develops in a world where a gentle push can send an object gliding across a room, where judging the arc of a tossed tool requires an intuitive understanding of a slower, more graceful parabola. This could cultivate a mind exquisitely tuned to trajectories and momentum, thinking in fluid, continuous curves rather than the abrupt stops and starts dictated by Earth's stronger pull. Their architecture would reflect this new physical poetry. On Earth, our buildings are heavy fortresses fighting gravity, with thick foundations and compressive strength as their primary concern. On a low-gravity world, structural engineering is liberated. Buildings could soar with a delicate, skeletal elegance, using tension and lightweight materials in ways that would collapse under Earth's weight. Lattice-like towers, vast, unsupported domes, and cities that climb vertically with a spiderweb's grace could become the norm, not as futuristic fantasies, but as the most logical and efficient way to build. Art and movement would be transformed. The concept of dance would evolve beyond the grounded, earthbound forms we know. A lunar ballet might incorporate long, floating leaps and slow, controlled spins that defy earthly physics, a celebration of the body's liberation from heavy restraint. Their sports would not be tests of raw power against gravity, but of precision, control, and momentum management. A game might involve guiding a sphere through a three-dimensional obstacle course in mid-air, using gentle touches and an intimate understanding of inertial drift. This altered relationship with the physical world could even reshape social structures and philosophy. On Earth, much of our history and metaphor is built on concepts of struggle, weight, and burden. We speak of heavy hearts crushing workloads and the weight of responsibility. For a culture born in a gentle gravity, where physical burden is minimized, their foundational metaphors might shift toward flow, balance, and trajectory. Their sense of self might be less about overcoming a constant downward force and more about navigating a field of subtle momentum. Their language could evolve new words for states of motion and orientation that have no direct translation on Earth. Ultimately, the brain's adaptability would forge a completely new normal, one where the technology, art, and very philosophy of an off-world civilization are not merely copies of Earth's, but organic outgrowths of a body and mind living in quiet, constant dialogue with a softer sky. For the first human born and raised on Mars, a journey to Earth would not be a homecoming, but a descent into a hostile and crushing world. Their body, a perfect machine for the gentle skies of their home, would face a physiological storm for which it has no defense. The crisis would begin the moment the spacecraft entered Earth's thick atmosphere and gravity reasserted its full, forgotten power. Their cardiovascular system, adapted to pump blood against a gentle slope, would be overwhelmed by the sudden, steep hill of Earth's gravity. Blood would pool heavily in their legs, their hearts straining to lift it upward. Dizziness would be immediate and profound, likely leading to a loss of consciousness unless they were reclined and medically managed from the very start. Simply trying to stand would be an impossible feat, their leg muscles and bone structure incapable of supporting their own Earth weight, which would feel nearly 3 times heavier than anything they had ever known. The act of rising to their feet could itself cause microfractures in their lighter, more delicate bones, particularly in the spine, hips, and legs, but the most terrifying assault would be on their senses. Their vestibular system, calibrated to the soft whisper of Martian gravity, would be flooded with a violent, undeniable signal. Their brains' carefully constructed map of balance, built on visual consensus and faint inner ear cues, would shatter. The room would spin uncontrollably, nausea would be relentless, and their own limbs would feel like alien, leaden weights moving through thick syrup. Every instinct for movement would be wrong. To them, Earth would not feel like a planet, but like a high-gravity prison. They would require constant medical supervision, likely needing to remain in a reclined or submerged position to alleviate the circulatory stress, and they might depend on powered exoskeletons just to achieve a semblance of mobility. The blue sky and green landscapes of humanity's cradle would be seen only through windows, a beautiful but deadly environment where their own biology had become their greatest liability. This reveals the ultimate irony of our expansion. The world that gave us life could become one we can never safely visit again, a home that permanently locks the door behind its children. This biological exile forces us to confront a monumental ethical choice. We are standing at a threshold where survival on a new world may require us to permanently redesign the human body, trading our universal adaptability for perfect, irrevocable specialization. The goal is noble: to give our children the best possible chance to thrive under an alien sky. But the cost is the potential fragmentation of humanity itself. Is this the ultimate expression of our adaptability, or are we guiding our own evolution toward a point of no return? When we consider genetic edits to strengthen bones for Martian gravity, we are not just treating a medical condition, we are writing a new chapter in the human genetic code. This moves us from healing individuals to shaping entire lineages for a specific environment. The ethical landscape here is profound. Who decides which traits are optimized? What happens if a future generation on Mars decides they no longer want the genetic legacy chosen for them by their ancestors? And perhaps most unsettling, does creating a human form that cannot survive on Earth represent a form of benevolent abandonment of our home planet? This is not a distant philosophical debate. It is a practical blueprint being drafted today in laboratories and mission planning rooms. The trade-off is stark. Becoming perfectly adapted to one world means becoming a prisoner to it. A Martian human with their elegant, lightweight biology would find the Earth a crushing, toxic environment, while an Earth human would be a fragile visitor on Mars, constantly fighting decay. We would be creating not just new cultures, but new biological realities, potentially closing the door between branches of humanity forever. This splintering raises a deep question about our identity. For millions of years, humanity has been one species, bound by a shared biology that arose from a single planet. If we successfully seed permanent populations on the Moon and Mars, and they adapt or are engineered over centuries into distinct forms, Are we witnessing the expansion of humanity or the deliberate beginnings of its speciation? They might share our history, our curiosity, and our dreams, but their bodies would tell a different story, a story written in calcium density, cardiovascular design, and gravitational sense. This could be the most significant transition in our entire history, moving from a single biological narrative to a symphony of human forms, each a unique reflection of the world it calls home. The path we choose now, between preserving a universal human form at great cost or embracing a future of deliberate biological diversity, will echo for millennia, defining not just where we live, but ultimately what we become. The gravity of our new homes will do more than shape our bodies. It will redefine the very meaning of human. This journey reveals a truth far deeper than engineering challenges or habitat designs. Establishing permanent settlements on the Moon or Mars is not merely a change of scenery. It is the activation of a slow, inevitable, and irreversible process of biological divergence. We are not just packing our bags for another planet. We are signing a generational contract with a new set of physical laws. The gentle, persistent pull of those alien skies will act as a sculptor, patiently reshaping the human form over centuries, from the density of our bones to the wiring of our balance. What begins as a physiological struggle for the first settlers becomes a new developmental pathway for their children, and ultimately, a distinct genetic legacy for their civilization. This is the profound and humbling reality of becoming a multi-planetary species. It is not about planting flags and building bases, but about allowing life itself to branch out, to follow a different evolutionary score played in a different gravitational key. We will not simply live on other worlds, we will become of them. Our biology will slowly mirror our environment, creating human lineages uniquely adapted to the gentle tug of the Moon or the dusty breeze of Mars. They may share our history, our language, and our dreams, but their physical experience of reality, the very data their bodies collect from the moment they are born, will be fundamentally alien to our own. This splintering invites us to look up at the night sky with new eyes. The question is no longer just can we live out there, but what will we become when we do? It challenges us to expand our definition of human beyond a single planetary blueprint. In a cosmic context, humanity may not be a single destination, but a spectrum of possibilities, a family of forms each perfectly tuned to the gravity well they call home. This future is being written in the mission plans and research labs of today. To follow this story is to witness the next great chapter in our species' journey. If you are fascinated by where we are headed and what we might become, be sure to follow along. The conversation about our future among the stars is just beginning.